I will start by saying thank you again to my co-organizers, John, Jose, and Sylvia, and to everyone who is here. I appreciate it very much. And so, in this talk, I will start my talk referring to what I call the philosophical foundations for a strong nomological interpretation of quantum mechanics. Then I will try to present you with some motivation from the quantum mechanics and undulatory formalism for that interpretation. And finally, I will try and suggest a possible formulation for the indeterministic and deterministic behavior cases in nature using a generalized version of the uncertainty relations. I will start with the question, how can we express the totality of cinematic behaviors of a particle in space? And there will be two possibilities extensively, and for that you will have to use the right properties. Let's say in abstract, the property P1 and P2, use the set of all values for P1 and for P2, and use the set of pairs of those values that occur simultaneously. The other way would be intensively, that is, formulate a general proposition involving P1 and P2 that would be valid for all the pair of values that occur simultaneously. So comments, law of nature can thus be ideally sought as having extensive and intensive representations, and a particle can be also sought as an acting agent, randomly performing behaviors from a set of possible ones. Now, how could a pilot wave framework suit the former comments? I will introduce you to the principle of solidarity. This principle says it was formulated by Bruno Finzi in 1955, and it says it is necessary to consider space-time to be solidly connected with the physical phenomena occurring in it, so that its features and its very nature will change with the features and the nature of those. In this way, not only as in classical and special relativistic physics, space-time properties affect phenomena, but reciprocally, phenomena do affect space-time properties. The ball is mine, of course. One does recognize in such an appealing principle of solidarity between phenomena and space-time that characteristic of mutual dependence between entities, which is peculiar to modern science. That is, how could a pilot wave in particular again suit comment C1 and C2? That is, that a law of nature can be sought extensively and that a particle can be sought as an actualizing agent. Well, one can suppose that the pilot wave, in a pilot wave framework, the wave structure surrounding the particle is a nomological structure, that is a kind of memory where all possible values of P1 and P2, the behaviors, are somehow codified. This also means that the particle would be able to decodify this nomological information and eventually produce new behaviors, altering the initial waveform and thus enriching, making it more rich, storing more information in it. And what is, in this context, the meaning of the word nomological? Well, it comes from the Greek word nomos, meaning law or custom, and relating in this context to the regularities which are not logically necessary, but that will become theoretically explainable by the enforcing of memorized habits encoded in the wave structure that surrounds the particles. Well, if one tries to apply the Finzi principle, originally sought for space-time, to the nomological pilot wave framework, it can become rather suggestive that as P1 can be considered position, that is space, in a certain sense, one can identify the set of all positions encoded in the wave with the space surrounding the particle. And in a stronger sense, space-time would then be equatable with the set of all possible behaviors encoded in the particles surrounding wave structure. That is, space would then be encoding all particles' behaviors. Of course, in this sense, that's one suggestion, space, wave, and nomological structure would all be names for the same physical entity. This means that in the nomological interpretation, I will suggest the quantum wave is not only a law-like entity in a purely idealized sense. On the contrary, It is to be thought as a nomological physical structure and as a physical carrier of nomological information, thus having an ontological value. It must be said that the idealized sense of the nomological approach was introduced by the Bohmian school as proposed by Detlev Dürr, Sheldon Goldstein, and Nino Zanghi. My view, on the other hand, is more resonant with the one endorsed by David Bohm and Basil Hiley in 1993, interpreting the wave function as a field of active information, although, as we will see, I will concede that quantum waves may be limited in space, making the wholeness property less stringent. Before fully initiating the nomological interpretation for quantum mechanics that I am proposing here, let me first address another problem, the configuration space problem. And as you all know, both in classical and quantum mechanics, we can represent an n-particle system using a generic point in an n-dimensional phase space. In classical mechanics, whatever function I choose to represent the system, it represents the global state of the system for a particular configuration of the n-particles. It is a description about the particles. In quantum mechanics, and I must stress in the suggested nomological interpretation I am proposing, the psi function will represent a physical and evolving structure that encodes all possible behaviors to be performed by the n particles. It is thus a description not about the actual particles, but about all their possible behaviors. In classical mechanics, the function, dependent on the n-dimensional position of the system, corresponds to an abstract description without any direct physicality of its own. For instance, one cannot prepare an experiment that will change the overall energy of the system prior to altering the individual energies of the particles. In quantum mechanics, again in the suggested interpretation, the psi wave, the psi field, if you want to, corresponds to a physical structure with undulatory characteristics that can be acted upon. For instance, one can prepare an experiment that gives rise to interference patterns prior to altering the individual kinematic states of the particles. Now, however, the problem remains that the dynamic evolution of psi must still be described in a multidimensional space, which seems to elude the physicality claim about psi. Can the strong nomological interpretation help solve this problem? Well, one possible answer would be using position as an example, since the multidimensional data now refers not to the actual positions of the n particles, but instead to all possible positions that each and every particle can assume. One may suggest what I call the encoding compression hypothesis. And it is the following: the dynamic evolution description of the psi field of the involving wave, the nomological structure, is strictly refers to the nomological information encoded in the physical wave and only coincides with the 3D wave dynamics for one particle. That is, all multidimensional nomological information is encoded in a compressed way in the 3D wave structure. So let me summarize this first section and state in full what I am proposing as the strong nomological interpretation for quantum mechanics. First, quantum mechanics is thus a second-order physical theory. It addresses the behavior of physical structures that encode nomological information, all possible behaviors of particles. It is thus a nomological information theory. The description of movements of the movement of particles and waves requires four properties: position, momentum, or what can be called state of movement, time, and energy. Properties X and P are a priori nomologically independent, that is, for each value X in a given X set, any value of P in a given P set of values can occur. Time and energy are also nomological independent. Properties, space and time, will be nomologically dependent, that is, for each value X in a given X set, only one value of T can occur, and in a given T subset. P and E are also nomologically dependent. Properties, space and momentum, are encoded in the nomological wave structure, and this encoded information is always active and accessible to the particles acting within the wave. Assertion 5, the last one, can explain the so-called state superposition when such states are mutually exclusive, since what is being supposed now is the physical nomological information of such states and not the states themselves. All possible values for X and P exist at all times as encoded information, although not as actual states of something, which will emerge only when they are actualized by the particles brought into existence, so to speak, from its informational condition to its actual state. Particles within the nomological structure interact randomly with it, change information, either retrieving information about already possible behaviors or enriching it with possible new ones. Observed physical regularities are the result of statistical emergence from an evolving nomological structure that, again, acts as a memory for a prior random undetermined behaviors that slowly builds up into a resulting distribution. The law-like regularities emergence may occur accordingly to a structural order increasing principle involving the weak teleology, and the encoding compression hypothesis is valid. There is nomological information compression from multidimensional data into a 3D structure. Finally, the average encoded values of P and E are related by a Schrödinger type equation describing the dynamic evolution of the encoded information as a whole within the nomological structure, which coincides with the 3D wave dynamics description for one particle. So, having stated the overall framework of this strong nomological interpretation, let me move on, suggesting further motivation for it from the quantum mechanics formulas. So let us consider the possible existence of a joint probability function F for a probability cumulative function F uppercase regarding the possible occurring values of properties P1 and P2, as given by expression 1 and 2. The marginal probability density functions result from 2 as the expressions 3.1 and 3.2. Now, how can we wave and code the marginal probability distributions for P1, let's say, equal to position, and P2 corresponding to momentum? I used the wave number, but of course it is momentum using the Broglie relation. Well, one possible answer is to use an encoding schema, such as the one in A41, where I call expressions 4.1 and 4.2 the encoding transformations, and where G is the marginal probability density for K, H is the marginal probability density for position, E and E prime are the encoding waves, the nomological structures, if you will, and C and C prime will be scaling functions, asserting the integrals as to give the right answer. It must be said that C and C prime are dependent on the spreading parameters of the Gaussian of the marginal probability distributions. And also it must be said that in each point X, G controls the relative weight of a wave carrier with value K, and hence the relative occurrence of the associated state of movement, that is momentum, in that same point X. And in a similar way, for each possible value of K, that is momentum using the de Broglie relation, H controls the relative weight of a wave carrier in position X, and hence the relative occurrence of that particular position nomologically encoded, one might say, in the same carrier. So we may now encode the Gaussian distributions using the prior schema for it. This will be using as encoding waves, plane waves, as you can see in 5.2. The scaling waves in 5.3 will be this, and most important, there is the encoding condition, which is 5.4, which will be very important, as we'll see. Please one will get 6.1 and 6.2, and recognizably, these are the usual transformations in the Fourier treatment. Please acknowledge that the encoding condition in 5.4, as I told you, can be written in this way, in this simple case, although in general, to obtain 5.4, one would have to take the modulus of psi and phi, since their sums would be waves. Now, it must also be emphasized that the use of plane waves as carrier waves is a direct consequence of the fact that these are solutions of the Schrödinger linear equation. However, it happens that in 2003, José Crocker formulated a nonlinear Schrödinger equation from the two basic classical balance equations, the Hamilton-Jacobi equation and the fluid equation of continuity, and for which the Morley wavelet soliton is the natural solution. For my own purposes here, I will be using wavelets with null average velocity and considered at time zero. I hope without stressing too much the main idea suggested. And please acknowledge that when the sigma spread term of the wavelet in 7.1 is very large, two things happen. On one hand, one gets an harmonic plane wave from the wavelet, and on the other, the nonlinear term in 7 vanishes, reducing the nonlinear equation to the usual linear Schrödinger one. Another important remark is that these quantum wavelets are in general limited in space, do not disperse, and have a well-defined spatial frequency. If we now use the same Gaussian distributions for X and P and the same encoding schema, but instead of plane waves, we use wavelets as the encoding carriers, we will get 8.1 and 8.2 in the second part of the slide. It must be realized that for the carrier wavelets, we have also a Gaussian distribution affecting their relative amplitude as they are used to encode X or K. This distribution is given by the sigma parameters, sigma X and sigma K. And of course, it is a kind of second Gaussian distribution that is at work. Now, you may wonder why I have considered this nonlinear Schrödinger equation and its wavelet solutions in this interpretation. Well, the reason has to do with the type of uncertainty relations that one can obtain from the encoding transformations using wavelets. You see, from 5.1 and 5.4, that is from the distribution, the Gaussian distributions of the values of properties for K and for X, and from the encoding condition, from 8.1, for 8.1, we can get this 9.1 very peculiar expression, which is an uncertainty general expression, well, more complex, which will be depending on sigma X, the spread of the wavelet carrier. And of course, we will have a similar thing in 9.2 for an uncertainty relations between space and momentum, which will depend now on the sigma K, which is the dispersion of the wavelet carrier for the information of for number wave. So the point to take here is that the two expressions 9.1 and 9.2 are of course not the same, and we have to twiddle it a bit. And that is, we have to enforce what I call the encoding density condition. And so if we do as is formulated in 10, where delta X and delta K are the intervals for possible values for X and K that can be nomologically related, that will be correlated, that is, that can occur simultaneously. And if we represent sigma X and sigma K as diversity ranges of the carrier wavelets for all possible values of X and K that can be encoded in the wavelets, after using the Pauli relation, we will get 11. 11 can now be considered the generalized form of the uncertainty relation for the position momentum pair. Of course, when the raw parameter is null, you will get the usual Heisenberg relation from 11. Please do acknowledge that by definition, delta x will be always lesser than sigma x, and that delta k also will be less than sigma k, and thus that rho is always less than 1. We can think about rho as a kind of encoding density or memory storage capacity for encoding physical information in the wavelets. To conclude, let me now present you with a possible formulation for the indeterministic and deterministic behaviors cases in nature using expression 11. To do that, we have first to give a nomological interpretation of the uncertainty relations. Suppose then that P1, cardinal P1 and cardinal P2 represent in the discrete situation the maximum number of values in the P1 set of values and in the P2 set of values. If that's the case, then the product of both cardinals is also the total number of possible values of P1 and P2 that can occur simultaneously. And then for any two subsets, P'1 and P'2 for their paired values, one will always have expression 12. And the first case, case 1, will represent the deterministic case relation between P1 and P2, meaning in the extreme case that for each value of P1, only one value of P2 can occur and vice versa, as given by expression 12.1. The second case represents the chaotic extreme scenario where for every value of P1, one would have every other value of P2 and vice versa, and so the number of all possible cases would indeed be n. Expression 13, the last one, is meant to capture the case where we have continuous intervals of values of property P1 and property P2. And this means that approaching 0 in 13 amounts to the same as approaching 1 in 12. That is, it means the existence of more structural order between properties P1 and P2, while going towards H would mean less law-like structure between P1 and P2. So if you now use, to perform as promised, the generalized uncertainty relation space 11 and place it in 14, as in this case, if one makes sigma x, that is the spread, make the wavelet very large and much more larger than the interval of values, and this will imply that sigma k will also be very larger than delta k, then the parameter rho will turn into 0 and we will have the indeterministic or Heisenberg's case. If one still takes rho as a kind of encoding density or memory storage capacity for encoding physical information in the wavelets, in this case, in Heisenberg's case, this would mean that the encoding wavelet is poorly populated and you will have chaos. So less nomological information would mean chaos. In the second possibility, which is when sigma x is near of delta x, that is when the, if you will, the memory of the wave is pretty populated, you will dense encode the nomological memory, as in 15.2, and you will have the deterministic situation, meaning the following, that for very small delta x, you can always find a very small delta k, and in the limit, you may have a one-to-one correspondence between x values and p values, and that's the meaning of this delta x, delta p approaching 0. This would be then the deterministic case or Newton's case. And with this, I conclude my talk. Thanking you all.